Breaking news from Clemson, South Carolina. My name is Taylor Hood.
And I'm Mary Grace Galloway.
And today we are going to talk to you about one of the most deadliest viruses in the world.
We are standing here in Clemson, South Carolina, where our sources may have identified an unknown case that could be the Marburg virus. Before doctors are able to make a diagnosis, they need our help to confirm this case. Starting us off with background and information, back to you, Taylor.
Marburg virus was first recognized in 1967 when simultaneous outbreaks of hemorrhagic fever occurred in laboratories in Germany and Serbia. 31 people became sick, with 7 people losing their lives. They determined that this outbreak was due to people exposed to the Ugandan imported African green monkeys while conducting their research. The signs and symptoms of Marburg virus, or MVD, start with fevers, chills, headache, and myalgia. Then around the 5th day, a rash may appear on the chest, back, and stomach. Nausea, vomiting, and chest pains may appear as well. Symptoms that have become increasingly severe can include jaundice, severe weight loss, liver failure, massive hemorrhaging, and multi-organ dysfunction. Since there are many symptoms, it can be difficult to diagnose MVD. This influences the high mortality rate, varying between 23 and 90%. Marburg virus can spread through human-to-human transmission via direct contact with the blood, secretions, organs, and other bodily fluids of infected people, as well as surfaces and materials including bedding and clothing contaminated with these fluids. So who is susceptible to this virus? People may be at risk or exposed to Marburg virus if they have contact with the Egyptian rosette bat or people/non-human primates infected with MVD. The Egyptian rosette bat is a cave-dwelling bat that is found widely across Africa and is the main animal reservoir for Marburg virus. Bats infected with Marburg virus do not show obvious signs of illness, which is another factor that leads to its high infectious rate. The most recent outbreaks this year occurred in February 2023 in Equatorial Guinea with 16 confirmed cases and 12 deaths, and in March 2023 in Tanzania with 8 confirmed cases and 5 deaths. Now that we've learned a little bit more about the background and general information of Marburg virus, back to Mary Grace to show us a little bit about innate immunity and how it helps to fight off the virus.
Innate immune system is the first line of defense against pathogenic viruses such as the Marburg virus. Macrophages use pattern recognition receptors to detect pathogens and activate downstream signaling to induce the production of pro-inflammatory cytokines and interferons. Let's take a closer look. Virus-infected dendritic cells will secrete type 1 interferons, which consist of interferon alpha and interferon beta, causing an interferon response which has 3 functions: to induce resistance to viral replication in all cells, to increase expression of ligands for receptors on natural killer cells, and to activate natural killer cells to kill virus-infected cells. Normally, retinoic acid-inducible gene 1 interacts with its downstream adapter molecule, MAVs, and activates 2 cytosolic protein kinase complexes, tank binding kinase 1 and inhibitor of nuclear factor kappa beta kinase. The TBK1 complex phosphorylates IRF37 and induces type 1 interferon production, while the IKK complex phosphorylates the inhibitor I-kappa beta, which activates NF-kappa beta and promotes production of pro-inflammatory cytokines. Marburg virus encodes a VP53 protein that binds to double-stranded RNA through C-terminal interferon inhibitory domain and prevents RIG1-like receptor activity, suppressing RIG1-like receptor signaling and therefore suppressing interferon alpha and beta production. Due to the suppression of interferon alpha and beta production, there will be decreased expression of natural killer cells because interferons function to activate natural killer cells. The Marburg virus can also infect and grow in monocytes, macrophages, and endothelial cells. Unlike dendritic cells, these infected cells secrete several chemokines and pro-inflammatory cytokines such as tumor necrosis factor alpha, interleukin-6, interleukin-8, and growth-regulated oncogene alpha CXCL1. This hyperactivation of immune cells causes a cytokine storm leading to high levels of inflammation, causing systemic damage and... Now to Taylor with B-cell immunity. Normally, B-cell immunity can be broken down like this. The B cells will circulate through the secondary lymph node and undergo 3 signals. The first one is an antigen BCR signal, where the naive B cell will bind to the follicular dendritic cell. The second includes the C3b complex, with a co-receptor complex and or a PAMP-PRR complex. These complexes are used to help indicate that an infection is present and acts as a co-stimulatory
to help bind a pathogen. In Marburg virus, MARV-VP35 is used as the viral polymerase cofactor. In the third signal, this involves the presentation of an antigen to the T cell in two different ways: T cell dependent and T cell independent. T cell dependent occurs in the germinal center, is when a B cell has a protein antigen connected to a helper T cell that can then undergo isotype switching to adjust for high affinity antibodies and make more memory B cells. In Marburg virus, isotype switching will occur from IgG to IgD, which is the immunoglobulin that will enhance mucosal homeostasis and immune surveillance by arming cells like basophils and mast cells. T cell independent has a polysaccharide antigen connected and requires multivalent bonding to the molecule. This produces mainly IgM and low affinity antibodies in short-lived plasma cells. Now back to Mary Grace with T cell immunity.
Normally, T cell immunity goes like this. An antigen-presenting cell, such as a dendritic cell, is activated by a pathogen that displays a pathogen-associated molecular pattern. Then the dendritic cells will express multiple receptors, then migrate to the lymph node. The dendritic cell expresses antigens on MHC molecules. The first activation signal is when the T cell binds to the MHC molecule. The second activation signal is when CD28 on the T cell binds to B7 on the dendritic cells. The last activation signal is the release of interleukin-2 cytokines from the T cells that bind to interleukin-2 receptors on themselves or other T cells. Some T cells will undergo more differentiation by more cytokine signaling. B7H1 is an immunoglobulin-like suppressive molecule. It controls CD8 plus T cell homeostasis and also contributes selectively to the deletion of intrahepatic CD8 plus T cells. As Marburg viral burden increases, there is virally induced upregulation of co-inhibitory molecules such as B7H1 on dendritic cells, followed by programmed cell death receptors on T cells, which leads to their apoptosis. We now know background information and different mechanisms on how the body fights off this virus, as well as how the virus impacts innate and adaptive immunity.
I think it's safe to say that we have provided enough information to effectively diagnose our patients.
Signing out, I'm Mary Grace Galloway.
And I'm Taylor Hood.
Stay safe, Clemson. Good night.